Having a robot that can glide in any direction, sideways, diagonally, or spin on a dime, isn't just cool, it's a serious upgrade in your robot's capability. In this video, I'm showing exactly how to build and program a Mecanum drive robot using Python from the first screw to the final line of code. By the end, you'll have a machine that's capable of full omnidirectional movement, and more importantly, you'll grasp the core concepts to tackle some even more complex robotic systems. I'm Brogan Pratt, and for over 10 years, I've been teaching robotics and technology, helping students bring projects like this to life. We'll start by building the chassis step by step. I'll guide you through the wiring, the motor controllers, the RC, and the Metro 4 Express. And then we'll dive into the Python programming to really make your robot drive precisely in any direction that you command. Let's go get started. Here's all the parts you're going to need. This is GoBuilda's Strafer chassis kit. I'm going to be building with version 5, but realistically the only difference is these bevel gears to version 6. So there's not a huge difference there. In terms of tools you're going to need a couple 3mm Allen keys, and then a 2.5mm Allen key. And then I like to use my little screw sorting box that allows me to grab a screw, runs it down, and sorts it into the correct side. Magnetic parts trays are also super handy to keep track of your parts so that you never lose them. Yeah, so first thing we're going to do is we're going to start building off the chassis. So let's grab one of these 17-hole U-channels, and we're going to grab a quad pillow block mount here. And we're going to go ahead and start adding in our center holes. We're going to count over 1, 2, 3, 4, 5, 6, 7, 8, 9 over. We're going to go ahead and mount our pillow block on the inside. We'll grab a 10mm screw here. And I like to just start with these hand tight until I can find the hole, because sometimes it can be challenging to get that hole in place. I got these first two started up at the top, and then this channel is really slick, because what I can do is I can slide my Allen key through the other side and actually tighten it up that way. Now, if this is your drivetrain, and you know that you're not going to be changing these at all at any time in the future, I would highly suggest, oops, that's the wrong hole. Highly suggest that you add a little bit of Loctite to these, because you do not want these bolts coming undone partway through your robot build, or your robot's going to be falling apart on you here. That is going to be a recipe for disaster. I'll throw the last one in there. I also really like these T handles as opposed to the L-shaped Allen keys. They make life so much simpler. Get anything started. Now that I've got that mounted on, we'll go ahead and do the exact same thing on the other side, but mirrored. So we're going to go over and count 1, 2, 3, 4, 5, 6, 7, 8, 9 holes. Put our pillow block on the inside, and rinse and repeat. Sometimes it can be a pain to get these first ones lined up. I always like to line up 2 screws as opposed to just 1 before tightening them in all the way. That allows me to make sure that I'm able to get these things nice and lined up. Get snug. Let's go ahead and repeat for the bottom 2. Some of my bolts have bad threading on them, which is why you're seeing me twisting in for about really challenging on some of them. I probably should have just thrown that bolt out. All right, now I got those nice and mirrored. We're going to go ahead and do the same thing, but do another quarter block down on the inside here. And for this quad block, we're going to go ahead and count 2 holes in. So we're going to mount it on the second hole on the inside like so. And the last one on this side. We'll do the same thing over on the other piece. Come on. Find the threads. You can do it. Oh, that's one that's being beaten up pretty good. Let's grab a different bolt here. All right. That's much better. With these quad blocks, you want to make sure you're not using too long of a screw. So if you use too long of a screw, what can happen is this bolt will actually go through these threads, like so. And you can't actually see it on this one, but you don't want it to be able to come through because eventually we're going to be mounting something on this side. So if you can see the end of this bolt coming through there, you've used too long of a bolt. I also like to be constantly rotating my design around. That makes life so much simpler for finding the correct angle to grab things. All right, now they're all mirrored up, we're going to go ahead and add in our side braces here. Now it's up to you at this point how wide you want your chassis to be. If you need this to be legal for a competitive robotics game, the widest you can choose is a 10-hole U-channel inside. I have found that something like a 7 or 8 works quite well for reducing the size of your chassis a bit if you're trying to get something a little bit smaller. But I'm going to go ahead and use an 11 here because it's what I presently have access to. I don't have a 10. And then we can go ahead and mount these 2 holes here and then these 2 holes here. Functionally, there's no difference between using a 7, 8, 9, 10, 11, whatever you want chassis here. It just depends if you have specific size constraints. I'll go ahead and use an 8mm screw here, and I'm going to go ahead and thread that in. Now here is where I like to use the ball head. Not only because it's a little bit smaller, but as you notice, the nice thing with a ball head on the end of this Allen key, it's got a little ball on the end there. What it allows me to do is instead of having to tighten this directly in line, I can actually rotate up and continue to twist and spin. And that saves you from having to take every single piece out. Oh, that is just clearly a bad screw because that's one wants to keep cross-threading. Let's try another one. Could also just be a bad mounting hole. Oh, it's just a bad mounting hole. Somebody has taken my part. Go ahead and change my angle here. Makes it a little easier to get some of these things in. And I can go ahead and thread this one all the way up. Oh, and that one's also cross-threading. Okay, let's go ahead and mount the other side on as well. You'll continue to be more and more thankful for this ball head as time goes by, especially on these awkward angle parts. I'm actually going to flip this upside down. Make it a little easier for me to get these last couple in. And sometimes you might need to switch to the other side of the Allen key to be able to help you get in all the way. Okay, give them a little snug, but don't have to be crazy snug. Let's go ahead and repeat the process on the other side here. Come on. Sometimes you need to push against the unit a bit there because the aluminum will flex out a little bit. It makes it hard for you to get it out of the way. Really got to make sure that you're putting these in nice and straight, at least at the start. Because you're working on such an angled piece, it's going to be really easy to cross-thread these, as some of my students have. And I'm currently building this with some parts that students had previously been working on. And because of that, I've got some cross-threaded sections. Okay, let's go ahead and flip it over. Put in the last couple. Make sure you don't miss any of these screws here. You don't want your chassis to not be fully constrained. Especially because this is the part that's going to hold your whole robot together. And the very last screw in the chassis. All right, so at this point, double check you've got everything in, Shep. 2 here, 2 here, 2 on this side, and 2 on that side. All right, at this point, let's go ahead and put it back upside down. Now with our chassis done, we're actually going to go ahead and assemble in our axle or shaft that's eventually going to hold on to our bearing. Effectively, what we're going to do is we're going to take a couple flange bearings. We're going to slide them through the shaft. I wouldn't do this right now. And then these ball bearings are what our wheel is going to slide on top of. So all ball bearings have that flange on them. And for this, we're going to make sure the flange is on the outside of the chassis. So I'm going to count in 2 holes, put in my 8mm ball bearing on this side, the flange facing out, and I'm going to grab that 6mm inner diameter facing the other side. Go ahead and take our shaft now, slide it through. You can take your beveled gear and slide it onto that shaft as well. I like to hold this ball bearing with my other hand, and now we've got nice, smooth motion here. Go ahead and grab a 10mm M4 bolt and an M4 washer. Slide that on like so. And what this is going to let us do is this washer lets us sit on the inner race of our ball bearing here. So we've got this ball bearing, And you have two races. You have your outer race and your inner race. And when you slide that washer on, it allows you to sit on top of that inner race so you get nice, smooth motion. So we're going to go ahead and screw that in to the end of our shaft. You can probably get this started hand tight, and then you're likely going to swing around, otherwise you can just start spinning. Go ahead and hold your shaft here, and now you can tighten that up. I would recommend you use Loctite at this point, so that this doesn't come undone. You should have nice unrestricted movement. Now it comes time to constrain down our gear here. And with our gear, you want to make sure you're not sliding against the aluminum here. You want to be off just a little bit, not a ton, just about a hair, because otherwise you're going to start grinding in. As you can see, somebody assembled this one incorrectly before. There's actually they've actually ground down the aluminum in this piece. There's a couple set screws here. We can go ahead and grab our 2.5 millimeter Allen key. I'll grab the 3. Again, making sure you have just that little bit of gap in between the wall there. And you can go ahead and tighten that down. And there's 2 set screws on here. I need to find a second screw for this, but I would say tighten down both because it's just a tutorial. I'm not going to bother with putting down 2. And I should have, again, unrestricted motion. You should hear no grinding. And we're off the races. Let's go ahead and repeat this 4 different times across all of our 4 corners. Grab my shaft again. Grab my miller. Count in 1, 2. Slide through. Grab my other bevel gear. Slide through all the way. Grab my 6 millimeter inner diameter. 10 millimeter screw and washer. And tighten that up. Again, you should definitely be using Loctite at this point. There we go. Check my motions nice and smooth, and it feels like I've got another bad ball bearing. Yeah, I can hear some grinding in there. So I've got a bad ball bearing. I'm going to swap that ball bearing out. So I don't like that one. And check that you've still got nice free of motion. I do. Nice and smooth. Now at this point, I'm going to back that bevel gear up just a little bit away from the edge so that I'm not grinding onto that aluminum. And we've got the 2 set screws to do up on this one. Check again, I've got nice smooth movement. I'm not hearing any grinding. Good. Go ahead and get the other side ready. Now on this side, we don't have our inner millimeter diameter ball bearings anymore. That's a good ball bearing. Oh, forgot my bevel gear. And let's grab our washer, 10 millimeter screw. And again, I would Loctite this one. This one's going to be a little bit more annoying to get in. So sometimes I'll even twist the shaft here as a way of threading in to my bolt. Makes life a little bit easier, especially when you're working in these super tight places. So I'm actually twisting the shaft here to be able to get ourselves nice and tight. Again, grab that bevel gear just a hair back. Go ahead and set on both set screws. And let's do the last side over here. Check my ball bearing again. Yeah, that one feels good. Let's grab our last one here. Mount through. Grab our last 10 millimeter screw. And I'm just going to go ahead and twist that shaft again. That makes it nice and easy for tightening it up. Hold that in there with the Allen key. Give it another little twist. And I'm good to go. Nice and smooth. Let's set up that last set screw. Oh, sorry, the last 2 set screws. Back it up a little bit. There we go. Check my movement again. I'm nice and smooth. Now we're ready to start adding motors. So I'm going to go ahead and place this to the side for now, because we're ready to start doing our motor assembly. A sub-assembly for our motors. Now, GoBuilder recommends that you use 312 RPM motors. If you're going to be using this, 312 is kind of a nice middle ground between how heavy your robot can be and how fast you get performance. In my experience, if you use a 435 motor, you're going to get a much faster chassis. You could even go down to a 223. That's going to increase your torque. You might be able to lift a little bit more. Depends on how heavy your robot is actually going to be. But for this tutorial, I'm going to use the 312 RPM motor. So I'm going to go ahead and grab one of these quad blocks again. I'm going to put these jet out places away from the motor. And we're going to go ahead and mount this down to our motor with a couple 11mm screws. I would definitely be Loctiting these ones because your motors are going to face a lot of vibrations as they rotate in and out and as they stop and turn and back on, just for the nature of what a motor is. So you definitely don't want these screws backing out on your build as you're going. Okay, one more. You can notice I'm assembling this in a cross pattern. That allows you to make sure that I'm nice and flush as I'm going down. Now, we're going to take 3 8mm shims. We may need more, we may need less. It depends on our system. We're going to go ahead and slide these 3mm shims on. I'm actually going to slide 2 on. Then I'm going to take my 12mm spacer. This does come as an aluminum spacer in your kit. I'm going to be using a plastic spacer here I 3D printed. Doesn't really matter for this case. And I'm going to throw one more shim on just to make sure that that metal is not going to be scraping against my plastic shim. And now I can go ahead and grab my last bevel gear, slide it on top, and that should be the exact height that I need to be able to mount everything up. Nice thing with this system is you can see with the screws for mounting my motor on, because I've got these nice holes in the bevel gear, I'm actually able to tighten up those motor screws later on if I need to. So I'll go ahead and tighten this down. You don't have to. I'm getting mine nice and snug up against those shims, so that's not going to come undone. And we might need to adjust the length of this later on in time. But for now, I think this is going to be good enough. Let's go ahead and recreate this sub-assembly 3 more times. So you've got 4 motors in total. I like to start a couple hand tight just to make sure I can line up the holes themselves. And then once I've got the holes nice and aligned, then I can go ahead and snug things up. Because it can be a right pain getting things aligned properly. Again, I'm using my 11mm screw here. We'll grab 3 more shims. If you were using a GoBuilder shim or the aluminum spacer, you'd put all 3 on at this point. I'm going to put 2 and then 1 just to make sure that I am backed off appropriately. Grab my other bevel gear, place it on top. Give it a good little snug with a 2.5mm Allen key. And let's keep going. Let's go ahead and put 2 more shims on. I'll put on my plastic spacer, then another shim. Second last bevel gear here. And our last system. And then our 3 shims again. Lost my spacer. I'll go ahead and snug this up. Alrighty, now we've got our motor sub-assemblies done. Let's go ahead and put these motors to the side. And grab our chassis back. And for this one, we can just go ahead and drop our motor in. We're just going to slide it in, like so. Slide it forward, and then we might need to wiggle these things to get our gears meshed up. And we should have our holes lined up like so. Right here is where we're going to line our holes. So we're going to go ahead and grab our 11mm screw and go ahead and tighten these in on all 4 sides. You should definitely use a Loctite on these ones. You may need to give this a little wiggle, a little bit of tweak to be able to align your screws up, and you definitely don't want to be cross-threading these. Go ahead and give that a little torque till we can get that in. And the other side in. So there we go. Now let's go ahead and snug these up. Oh, and both of my screws have come out. Excellent. It's okay, my hole's already lined up, so I'm ready to rock. Okay, and the last one. Alright, now comes a good time to check if your motors are properly aligned. You should have a little bit of backlash between your gears, but not too much. So a little bit of backlash, and what I mean by backlash is when you take this and you rotate a little bit, notice there's just a bit of that backlash. There shouldn't feel like there's a lot of resistance between your system here. If there is a lot of resistance, likely you need to back this up a little bit. So you probably need to take one of the shims out of this system. So you can go ahead and take your bevel gear off. You might need to take this whole subsystem out, take out one of your shims, and then realign it again until you have a nice system. Let's go ahead and do the same thing on the other side. Slide that in, press it up. I like to get all 4 of my screws somewhat hand tight in first to make sure I've got my holes aligned before I go about trying to snug everything up. That's just a bit of a safety thing, mostly because I've found that it can be hard to align some of these sometimes, especially if you have all 4 tightened up at the same time. Give this a little rotation test. Get a little bit of backlash. And that's looking pretty good. Let's repeat it for the last 2 sides. I really like this internal motor mount system. I think it's really slick. It gives you a lot of space to work with on top of your chassis. There's tons of room for fun and activities. Just another little test. A little bit of backlash. Doesn't feel overly challenging. And then let's do our last subsystem. Now on this one, you want to make sure that you're putting your motor cables up. You probably don't want your motor cables facing down. If your motor cables are facing down, you're going to have a harder time accessing those odometry pods. Odometry pods inside these GoBuilder motors effectively allow you to keep track of how many rotations that a motor has done. And it can be useful to know how far your drive motors have moved. That last screw. There we are. Okay. Now we've got all 4 of our motors settled in. Got a healthy amount of backlash going on each of those. We should be ready to rock. Now, when it comes to your wheels, there is a left wheel and a right wheel. If you look inside here, one of these has a shallow end and one of them has a deep end. So if we look at the 2 deep ends looking together, you'll notice that they actually rotate opposite from one another. So this side, oh, actually, I think I grabbed the same. There we go. This is a better example. So if you look at it, I grabbed 2 of the same. These ones are actually rotating opposite from one another. So what we want is, we want to flip our chassis over. And when I'm looking down at the chassis, I'm going to set this up a little bit higher so we can see. I'm looking down at the chassis. I want the 4 wheels to be facing inwards in a X-shaped pattern. So if I look at this chassis and I'm looking at it straight down, you want to notice that these little black rollers are drawing a line towards each other so that it shapes in the letter, makes it X or diagonal when I'm looking at the chassis from the top down. You have to have it in that orientation. If you don't have it in that orientation, your design will not work and you will not properly strafe. Let's go ahead and actually assemble these in. All these wheels, we've got the deep side and the shallow side. The shallow side should be facing the chassis and the deep side should be facing out. And on these shafts, one has a slot without a threaded holes, and then this hole here has threads inside. So those are the ones we want to line up against. So I have the deep side facing out. I'm going to grab another 11 millimeter screw and a 4 millimeter washer. And we're going to go ahead and mount these on. Anytime that you're mounting something to plastic, you want to be using a washer to help spread out some of those forces. I like to pre-make my washers here. Go ahead and put the shallow side against the system. Line up screws. Let's see, there we go. I'm not going to thread these ones on all the way yet because I want to make sure that I'm nice and aligned, especially at this point. And you should definitely Loctite these, especially because they are your wheels. So I'm going to go ahead and tighten this down in a cross pattern. using a cross pattern allows me to make sure that I'm nice and flush and level. And there we go. There's our first wheel. Let's go ahead and set up our subsystem for the next wheel. Go ahead and take all my washers, put all my screws of the washers on them. All right, we're ready to put the next one. Do a sanity check. Make sure that I'm still doing that X-shaped pattern across. In this case, I am. So the shallow side, deep side's facing out, shallow side's facing in. Let's go ahead and mount this one on that last piece as well. Start with just finger tight. Before I go ahead and actually fully tighten this in all the way. And that cross-shaped pattern. We'll grab that one later. This is where assembling things next to a camera can make life a little bit difficult sometimes. Okay, got that side on. Let's go ahead and mount up the other side of the system. Now I'm going to make sure that I grab these wheels, associate them with the correct side as I rotate this around, so that I'm not forgetting which wheel needs to go in which place. I'm going to go ahead and make up my washer systems again. I like to pre-thread my washers on. It makes life just so much easier than having to try to fight, or not fight, but having to go back, grab another thing. Just adds an extra step. I think just makes life a little bit more efficient here as I'm placing this on. I'm all about trying to find those little bit of efficiencies in your builds, and it's amazing how doing things in batches can really help speed up your building time. You don't have to over-torque these things. If you're over-torquing these wheels, you're actually going to start compressing those washers into that plastic backing on the wheel, which is not necessarily something that you want. And on to the final subsystem. Again, shallow side facing in. Go ahead and place this on like so. I can find my threaded hole. There you go. And last one. You can also definitely Loctite these in batches. That can make your life a lot simpler too. Now we've got all four ready. Sometimes you strip some threads. That's all right. We just throw those bolts out. Keep them in a separate location. Do not add them back to the bolt pile. Otherwise, this happens. Alrighty. Some last final checks as your substance just about done here. We want to check. I'm going to go ahead and lift up. I'm going to grab this wheel. I'm going to push forward and backwards. I'm going to try to see if I can move the wheel in. I shouldn't have any slop in this one. That one's good. That one's good. This one's good. And this one's good. If you do find you have slop, you can use a small 6mm diameter, 4mm diameter shim here. It's a very small shim that they include here, like so. What this shim can do is it can go in between this screw, your washer, and this shim to be able to add you up a little more space. What's going to happen sometimes is that sometimes these can be machined slightly differently, or this aluminum chassis can flex a little bit, and it's not going to stay in nice and tight. I'm also going to go ahead and check each wheel again. I should have a little bit of backlash. Can you hear that? You can see that I can move this a little bit. That's what we want. We do not want zero backlash. If we have zero backlash, that means we have too much friction on our wheels. Let's go ahead and check this one. That's pretty good. And it turns freely in my hand. Check this one. Turns freely in my hand. Oh, this one might have a bit too much friction on it. Oh, no, there we go. Okay, no, this one's good too. Actually feels like I might have put a bad ball bearing in on this one. Yeah, I think I'm going to swap out that ball bearing. It sounds like feels like I've got a bad ball bearing. Okay, but other than that, that's how you assemble your all-in-one drive. All right, so let's talk about what kind of electronics we're going to use. For our microcontroller, I'm using a Metro M0 Express. I've also used Metro M4 Expresses in the past. This is a great little board because it's the same form factor as Arduino, but it allows you to program in Python. Our motor controller is the RoboClaw 2x30 amp. A 2x15 amp would also work. Even a 7 amp would work. Just depends how big your robot is. In this case, I'm using 2x30 amps because I'm pumping through a lot of power. In terms of the mode settings in this, it's going to be mode 1, option 4. And you can set those using these specific buttons here. I have 2 of them because it's only able to control 2 specific motors. You've got power in, you have motor 1 and motor 2. I'm going to be using a 12-volt battery pack as my main battery source for the DC motors. And then I'm going to be using a 9-volt battery pack for controlling the microcontroller itself. As far as all these wires and things go to be able to connect things, I've got the bullet connectors that connect to DC motors. I've gone ahead and put on a few ring terminals here, and that makes it just a lot more secure when we're connecting it to our motor controller. For the controller, I'm using the FS-i6 controller here by FlySki. This is typically used for RC planes, but it works wonderful for setting this up. So for our DC motors here, I've gone ahead and ran the cables up through one of these center wires here. Be careful as you're running through. This aluminum channel can be quite sharp, and you don't want to actually cut your wires as you're pulling it through. Putting some sort of plastic collar or protector on around here is likely a good idea. GoBuilder has these little plastic collars here, but you can also 3D print them. So I'm going to go ahead and feed these through so that we end up with some nice protection for our cables. Because you definitely don't want to be scratching your cables to the point where you end up shorting out your motors because they have cut the edges there. There we go. Nice protection. Let's do that on the other side. With that all set up, next thing is our battery. Now with a Mecanum drive, you really need to make sure that your center of mass is directly in the center of the robot. If you have mass on specific weights or at specific points, you're actually going to end up strafing in a bad position or poor position. So you want to be as symmetrical this way and this way as you can. So I've got this little battery mount here that I'm going to be mounting on this side that allow us to get that 12-volt battery in like so. Now I'm just going to use some of our old friends, the cable ties or zap straps here to hold this in. Because trying to get a part through here is a gigantic pain. So using some cable ties is going to make our life a lot easier. Let's go ahead and loop that around. Give it a little pull as we twist it in there. And then same thing on the bottom. You might find that with the cable ties, if you take the end and you bend it like so, it allows you to get around some of those corners a little bit easier. Okay, our battery mount is all squared away. We can grab some little flush cutters and snip off the end of those cable ties. And we can put our battery in like so. Then I'm also going to use a cable tie through the end here to stop this from coming out. And actually, instead of cable tie, I might use a piece of Velcro. Cable tie and Velcro are some of my greatest friends. They are awesome for cable management with your robotics projects. This will stop our battery from sliding out of our holder as we go around. And then Velcro makes it super easy to take this thing out later. Beautiful. Okay. So with our battery in there secure, let's go ahead and put on our motor controllers next. Motor controllers, I'm going to go ahead and face. I want the part where I'm actually be connecting our motors in, like so. And I'm going to, again, just use a couple zip ties here. I'm going to use my little folding trick so I can easier get that through. Push that through on both sides and line up my hole. And we'll, again, do that little folding trick. Get us through. Zip ties and cable ties. Velcro is a fantastic temporary solution for holding things together. And as much as you might think it is a little bit jank, perhaps, as opposed to using bolts, if it's good enough for holding things down on the European Space Station, it's good enough for your robotics project. Go ahead and clip those off. Now let's go ahead and put on our main control board. I'm going to put the main control board at the back here. Again, I'm going to be connecting this down with some cable ties. I love that little fold in the end of cable ties trick. And with my MicroController here, I've got a little mount that allows me to attach a breadboard to it. I find it super handy. Now for our main battery, we need to add in our switch here. So what I've done with my switch is I've simply just pulled out the positive lead, and I get a male Tamiya out to two XT male 30 connectors. So we're going to mount this in a place that would be nice and safe on our robot so we can easily access this at all times. I'm going to choose the back over here like so. You always need to be able to access your power button in the case of an emergency. So we're going to make it nice and easy to reach. Also, a big, bright red flashing button makes that fairly easy to know. We'll put in a second cable tie here. And maybe push up from the bottom. I'm going to fold that around, do a little double fold. Get that up and around so it almost makes like a J. So a little easier to get it up and through that main mounting hole. There we go. Oh. Spoke too soon. Not quite beautiful. Almost beautiful. There we go. With your battery supplies, you almost always want to have some sort of switched supply. Okay. And we're on there pretty good. We can go ahead and connect our battery terminal up now. Make sure our switch is off for now. And then let's go ahead and connect these to our RoboClaw controller. Now the RoboClaw controller here, I've got these little pinout points where I simply just have ring controllers out to an XT30. And that just makes it easy so that things are always connected strong. Now with these little screw terminals, I'm going to use a magnetizer. Allows me just to pull a screwdriver through. I can just lay it in, pull it back through. And it creates a temporary magnetic field so that I can have my parts not fall off the end here. So let's go ahead and screw on our XT30 connections. For our battery. And it looks like I might actually need to get an XT30 extension cable for one of these. Make sure you definitely do -10 to negative and positive to positive on this. Otherwise, you'll end up blowing your motor controller. There we go. Let's go ahead and plug one in on this side. And then I'm going to have to go get an extension cable for that. Now, if you don't have a switch that already does things off on a Y, you can use one of these Y terminals. And I'm actually going to use this as my extension cable for now. Not best practice. Should be using a different extension cable so things don't come up. But because technically these are two live terminals now. So I'm just going to make sure that I Velcro these out into a safe location so that I don't have to worry about where it is that they're going. I think I'm also going to add one more zip tie to this power switch because I'm not putting this power switch in with some bolts. I'm going to make it a little bit more secure, like so. Beautiful. Let's go ahead and connect up our motors. Now with our motors, I've done the same thing. I've done those ring terminals over to our bare bullet connectors. You don't need to do this. You could technically just cut off these bullet connectors and screw them directly onto your terminal. I'm not a big fan of doing that though, because these ring terminals, especially with these robotics projects, I like to take them apart and rework them again. Makes life a lot easier. Now on your RoboClaw controller, you have an A and a B section. You have M1A, M2B, and then B and A, and they are reversed on each other. So B is the inside on both, and A is the outside on both. Again, with a DC motor, it doesn't actually matter which side you run things to. What matters more is on a DC motor, you can actually have these things. When you reverse the player, it just reverses the direction of the motor. So for my ease, I always like to say B is ground and A is positive. So I'm going to screw on our screw terminals, assuming that logic. Grab another one of those. Watch that you're not grabbing your cables up and under on things so that you are always making sure your cable management is nice and clean every time. You don't want to try to have these things be gigantic jumbles of wires. So don't just put things wherever it is you're feeling. Notice how I'm not connected through my battery. Let's go ahead and spin this around. We'll do the other side now. Again, B is going to be our ground terminal for now. And then our last cable here, underneath my power cable. I'm using M3 ring terminals. Oh, I'm a little bit cross-threaded there. There we go. I'm using M3 ring terminals because that is the size of the screw for my RoboClaw controller. There we go. Now that's all set up. Let's go ahead and actually wire up these DC motors. Now looking at our motor here, I'm going to make this motor controller and side control the right side of the robot, this side control the left side of the robot. Now, typically when you wire up a Mecanum drive, the right side is inversed, and you inverse it in hardware so that you can program everything using positive values in your code. It may seem a little bit confusing now, but it's going to make it a lot easier to program later. So on the left side of our robot, we're going to grab the front motor. What I like to do is I like to look down in the bottom and I give it a little wiggle. And when I give it a little wiggle, I can see which motor it is that I'm working on. And I'm going to connect this one to motor 1, which is going to be actually the closest. Is it the closest side? Yes. Motor 1 is the side closest to us. So I'm going to connect red to red and black to black. And on the other motor, I'm going to make sure I don't get myself all tangled up. I'm going to get to the motor 2, and I'm going to go red to red and black to black. Now on the opposite side, I'm going to do that in reverse. So I'm still going to give a little wiggle so I can see which motor it is I'm grabbing. My front right motor is going to go to motor 1 still. which in this case is going to be the far one. But this time, we're going to inverse that polarity. So we're actually going to go red to black and black to red. And all that's going to do is that's going to reverse the direction of our motor, make it way easier to program. Do the same thing over on this side. Again, red to black and black to red. And let's go ahead and cable manage these out of the way. Velcro is one of my favorite tools for cable management. We'll just go ahead and loop these all up into each other. Grab a strip of Velcro. And we'll just run it around itself. The reason I like Velcro is it's super temporary. Cable ties are not really fast for getting things done, redone, and undone. But Velcro makes life so much easier. Again, just like cable ties, while you might not think that Velcro is an intense tool to use, if it's good enough for the International Space Station to hold astronauts while they sleep, it is good enough to hold your motor controllers in, provided you're actually using a decent strip of Velcro. Alrighty, those are all up there, looking nice, looking a little more pretty now. Now let's go ahead and actually do our wiring for everything else. So let's do the wiring of our FlySki controller first. Now in our FlySki controller, this setup, you have your channel 1 all the way up through channel 6, and the top one is your battery and voltage. On this controller, you have an iBus, and then you have your PWM outputs. We're going to be using the PWM side. And I've made up a quick little chassis harness here that allows me to pull out channels 1, 2, 3, 4, 5, 6, and then output them over to the other side. So with this one, I can actually go ahead and wire this in nice. So now I have my signals for our power on this side, and then we have our 5-volt and our ground for our main motor controller. This one's also Technic compatible so that I can push this on like so and not have to worry about things flying away. Actually, I'm going to go ahead and wire this up over here. Beautiful. We're ready to rock. Now I can go ahead and do our, for me, orange and white is 5-volt and ground. So I'm going to connect this to 5-volt and ground, our motor controller. And then I'm going to, for me, brown and brown-white are channels 1 and 2 respectively. So I'm going to go ahead and connect these up to channels 13 through 10 on my connector here. And then I also have a channel 4 that I'm connecting to digital 9. I'm not going to connect channel 3 today because I'm not using it in this project. Now let's go ahead and connect our RoboClaw controller on. Now for our RoboClaw controller, we're only going to use 3 ports here. At the start, down here by our serial ports, we have our S1, S2, and then ground is going to be this far side. So I'm going to go ahead and connect S1 and S2 and do the same thing on this side, S1 and S2, and a ground so we can get back to a common ground over here. So let's grab some jumper cables. Now this motor controller, remember this one's controlling the left side, and motor 1 is the front left. So I'm going to go ahead and do servo 1 over to digital 0 on our microcontroller. Then I'm going to connect servo 2 or S2 over to digital 1 for our rear right. Oh, actually, so I'm going to go digital 2 on this one for the rear left because I'm going to use the front right motor for that one. And then we need to get a ground. So I'm going to go ahead and grab a ground. At any point along this ground rail, this far right one is fine. We'll connect it to a ground on our Metro board. I'll connect to the ground up here. We're going to have to actually cable manage that out of the way. Otherwise, we're going to run into those all day. So let's go ahead and just tie up these points for our battery so that it doesn't get in the way, like so. All right, we are. That's the exact same thing on the other side. Let's grab that S1 again. We're going to connect this one to digital 1 because it's going to be our front right. And then S2 over to digital 3 for our rear right. And then we also need a ground again on this one. So we're going to just grab a ground pin. Doesn't matter which one you choose. Coming over to a common ground on our Metro board. Now, last thing I'm going to say is having your radio receiver here directly by a battery and directly by a motor controller, it can produce a lot of electrical noise. I have not found so far with this project that does meaningfully impact this, but if you do find it is meaningfully impacting it, move your radio receiver further away from your motor controllers because your motor controllers are quite noisy with sending out signals. Last thing we need to do is do up our battery, our 9-volt battery. Again, I'm going to use our old friend Velcro here just to hold on. Oh, that Velcro is too short. Let's grab a longer strip here. I'm going to go ahead and hold on our battery pack so that things don't go flying away on us. So we got our 9-volt battery pack here. We can go ahead and connect that to our DC controller. And we're now all wired up. So let's head on over to the computer and let's start programming this. So over at our coding program, let's take a look at how we're going to break down our steps for today. So our programming steps today are, 1, we're going to have to set up our RC controller so we can have our inputs. 2, we're going to set up our DC motor controllers. We're going to have to set up, or we're going to have to create a helper function that converts milliseconds to a duty cycle pulses. We need to do that because our motor controller assumes you have a 400 milliseconds of range, but we need to convert those into duty cycle pulses because that's actually how we're going to control our motors. After that, we need to create a helper function that normalizes the joystick input. And then finally, we're going to create a drive function that takes our normalized inputs and outputs Mecanum to drive motor commands. So let's start with that first part where we need to actually set up our RC controller. First thing we do, as usual, is we're going to import time. We're going to import board. And we're also going to say from RC, import RC. So this is a class you can find in the library down below that allows us to use the FlySki FS-1 or i6 controller with CircuitPython or Python. And we're going to create the RC object. And this was simply going to be RC equals RC. And then here's where we create all of our different channels. So we're going to be reading channel 1, and this is going to be board.D9 in my case. So actually, sorry, this is D10 in my case. Channel 2 is equal to board.D11. Channel 3 is equal to none because we're not reading channel 3. And channel 4 is equal to board.D9 in my case. Channel 5 is equal to none, and channel 6 is equal to none as well. Oops, not equals. So that is our RC object initialized. If you'd like to have more switches, you could go ahead and actually import these channels. But so in this case, we're not actually going to be doing that. Then let's actually read our channels, and this is pretty easy. So we'll say while true, we're going to say our throttle is equal to rc.read_channel, and our throttle is the y-axis on our right joystick, which is channel 1. Our strafe is equal to rc.read_channel, and our strafe is actually going to be channel 2. Then finally is our rotate, and that is equal to rc.read_channel, and this is going to be channel 4. Now at the very end of our loop, because we're reading on that RC, on the specific controller we're using, we are reading PWM cycles, and we need to stay within a PWM loop. So I'm actually going to put in a time.sleep for 0.02, and this keeps us in cycle with the PWM of the RC controller. We've now set up our RC controller. We're ready to rock. Let's go on to the second step, which is setting up our DC motors. Now for our DC motors, we need to import another library. We're going to import PWM IO, or pulse width modulation in out. And let's actually create these 4 different objects. So we're going to create 4 motors. We're going to say motor_front left is equal to PWM IO.PWM out. And this one is going to be, our front left is board.D0, and it's got a frequency of 50. We're going to create this for our front right, our rear left, and our rear right. And thankfully, using Copilot, it's actually pretty smart here. These are all actually correct. So we've got our front left, front right, rear left, and rear right, all to our respective motors. Now, before we continue on, we need to set up some default ranges so we know where we are actually at. Using the roboclock controller over serial output, the stop milliseconds is equal to a 1.5 millisecond pulse. So if you send a 1.5 millisecond pulse to a motor, it's going to stop it. Our max milliseconds speed is going to be 1.9, and our min millisecond speed is equal to 1.1. So we actually have a 400 millisecond range, plus or minus, to control max power of the motors. You might want to check the documentation on your motor controller to make sure yours is the same, but for my motors, this is where things are going to be sitting at. So now we've got our default set up. It's time to go ahead and convert those millisecond pulse commands into a duty cycle. We're going to use a helper function to do this because the duty cycle is going to be a full 16-bit analog range, which means we've got 65,535 values to work through, which is why we're using these millisecond cycles as opposed to having to type it in. So we're going to create a new function, and we're going to say millisecond to duty cycle. And for this, we're just going to assume a frequency of 50 because we've already done so. So we're going to say it's going to take millisecond as an argument. It's also going to take frequency as 50. First thing I'm going to do is I'm going to take a period of milliseconds is going to be equal to 1.0 divided by our frequency multiplied by 1,000. And then to actually get our duty cycle is equal to an integer division of our milliseconds divided by our period milliseconds divided by 65,535.0. So that gets us our duty cycle number. Now we need to make sure that the duty cycle that we send is in between the ranges of 0 and 65,535. So the last thing we're going to do is we're going to do a quick clamping helper function. So we are going to return the minimum of 65,535 and the maximum of 0 and our duty cycle. So this just clamps the duty cycle from 0 to 65,535. Effectively, how it does that is first it's going to calculate the maximum value between 0 and the duty cycle. It's possible that our duty cycle gets calculated as a negative number, in which case the maximum we should take is a 0. And then it's going to take the minimum number between the absolute maximum value and whatever the value was here. So it's possible that this duty cycle ended up being 70,000. Then it's going to take that minimum number between those two. So it'll always pull between 0 and 65,535. So next is one of our really important helper functions. We're just going to create a stop all function. It's really useful in robotics to have something you can use as sort of your red button if something goes wrong. So let's create that. So we're just going to find stop all motors. It's not going to take anything. And whenever we call this, we're just going to stop everything. So I'm going to say motor underscore front left dot duty cycle is equal to our milliseconds to duty cycle function and then stop milliseconds. We're going to call that down for all of our motors for our front left, our front right, our rear left, and our rear right. So whenever we call that stop all motors, it's going to send that millisecond to duty cycle helper function with our stop milliseconds, which of course is 1.5. So this should stop all of our motors. Important thing about this roboclock controller is whenever you send a command to it, the motors will continue to run. So if you don't send a stop command, they won't actually stop. So this is a really useful function. At this point, we've set up our RC controller, we set up our DC motor controllers, and created the help for our function that helps us convert those milliseconds over that duty cycle. Next, let's go ahead and create that helper function that normalizes that joystick input. The reason we have to do this is with the RC controller that I'm using, it expects a range of 0 to 100 from the joystick. However, in order to control Mecanum wheels, Mecanum kinematics expects between negative 1.0 all the way up to 1.0. So we need to be able to normalize that input value from 0 all the way up, or from negative 1 all the way up to 1. So let's go ahead and create that function. So I'm going to say define normalize input, and we're going to take a value as our parameter. Now, the first thing we need to do is we need to set up our dead zone. And what a dead zone is you'll probably find that with some controllers, that center joystick doesn't really bring itself back all the way to center. We would expect that 50 is the center, but sometimes when it releases back, it's not always back to that center. So we're actually going to say dead zone min is going to be equal to 45, and the dead zone max is going to be equal to 55. And then we'll check if our value is within those dead zone mins. Before that, we're actually going to check if the value is equal to none. We're simply going to return 0. The problem, so if our value is equal to none, we're going to return 0. What this does is if we pass in a none value, and that will get exported, or that will get returned with that RC controller, it returns none if it gets an invalid reading. So this allows us just to stop the controller. The 0.0 is going to end up actually creating a stop for us because that's our mid value. Then we're going to check if our value is inside that dead zone. So we're going to say if the dead zone min is less than or equal to our value, and our value is less than or equal to our dead zone max, so our value is in between our dead zone, we're actually going to go ahead and return 0 again. So a lot of stopping functions, but again, robots are all about safety. So now that we know that our value is going to be in that dead zone, let's actually see what happens if we are pulling back on that controller or below our dead zone value. So we're going to say elif the value is less than the dead zone's minimum value. We're going to return our value minus our dead zone min divided by our dead zone min. So effectively what this is going to do is it's going to turn whatever that value between 0 and 44 is into a decimal number between negative 1.0 and 0.0. Then we're going to say elif our value is greater than our dead zone max. We're going to return our value minus our dead zone max divided by, this time it's going to be 100 minus our dead zone max. And this is going to do the exact same thing. It's simply going to return above 55, and it's going to convert that 1.0. So at this point, we've now got all of our helper functions set up, and now we can actually finally go ahead and create that drive function that's going to go ahead and move our Mecanum wheels. So we're going to go ahead and say define drive. And our drive is going to take 3 parameters. We need to take our throttle speed, we need to take our strafe speed, and we need to take our rotate speed. And so we're actually going to one more. We're also going to add in an input scale. And what an input scale does is it allows us to effectively change the sensitivity of those joysticks. So if you find, rather than having to change the joysticks themselves, you can change the 0.5. If you make it greater up to 1.0, it'll make it so you get an absolute transfer. If you bring it down, it makes it so that your joystick command doesn't go as fast. It'll make things a little bit less jumpy. It's nice to have a bit of proportional control in here. This is future Brogan coming in to edit this. I realized I made a mistake there. It should be strafe, and now my whole function will actually work. I had accidentally wrote this as input scale in parentheses 0.5. It's actually input scale equals 0.5. Didn't catch that until I went through back and edited it. So first thing we're going to do is we're going to normalize all those inputs. So we're going to normalize our forward input, which is going to be our throttle speed, but we're going to put it inside our normalize input value. So we're going to say normalize input, and we're going to normalize our throttle speed input. We'll do the same thing for our strafe and our rotation. So I'm going to say that strafe is equal to, again, normalize input, but our strafe speed, and then rotate is equal to that normalize input, but our rotate speed. Then we're going to check if those values that we sent are within that dead zone. So we're going to say if our forward is equal to 0 and our strafe is equal to 0 and our rotate is equal to 0, we're just going to call stop all motors and then return a null value. This is, again, another one of those safety functions. If your joystick happens to be in the direct center, you're not touching anything. When you're calling drive, of course, nothing should be moving. If those values happen to be outside of drive, let's go ahead and actually send those out. So we're going to multiply in our scale so that we can scale down some of that sensitivity. So we're going to say forward is equal to forward times input scale. Same thing for strafe and same thing for rotate. Now let's actually do our Mecanum kinematic equations here. So in order to do those equations themselves, we're going to send power to each individual motor. So we're going to say motor underscore front left power is equal to forward plus strafe plus rotate. Our motor underscore front right underscore power is equal to forward minus strafe minus rotate. And then our motor underscore rear left power is equal to forward minus strafe plus rotate. And then our motor underscore rear power is equal to forward plus strafe minus rotate. And I actually have a spelling mistake here. There we go. If you want a deeper explanation into how these kinematics actually work, I've got a video in the description down below about how these mathematics actually transfer those forces into directional movement for your Mecanum drive. But effectively, this is the quick equation that allows you to move everything out. Next, it's time for us to make sure that we clamp that power between -1 and 1.0. What you'll find is that it's entirely possible that you have a forward and a strafe value of 1 and a rotate of 0, and it's not possible to have a motor command that is greater than 1. The problem with that is you cannot send 200% power to one motor and 100% power to another because it'll only accept 100%. So we're actually going to scale everything down a little bit so that it clamps it between. And then if one of the motors is at 200%, one of the motors is at 100%, we're actually going to call the other motor at 100% and the other motor at 50% so that the ratio stays the same for what it is that we would expect the output to be. If we don't do that and we would want to go forward and diagonal, we'll actually end up not moving the direction that we want. So the first thing we need to find is we need to find which motor is currently the strongest. And the current max power is equal to the maximum of our absolute value of our motor front left power, then the absolute value of our motor front right power, absolute value of motor rear left power, and rear right power. We grab that absolute value because it's possible we have a negative 2.0, so it basically removes that negative and says whatever our current value is. Then Copilot is smart enough here that if our maximum power is greater than 1 or higher than that, we're going to scale all the motors down based on whichever power was the highest. So it's entirely possible that one of them is actually sending 3.0 value. So then it would scale everything down by a third. Now, the last thing we need to do is actually command the motors to move. So we're actually going to move the motors and convert to milliseconds. So we're going to grab our motor underscore front left dot duty underscore cycle is equal to, so we're going to actually send out that duty cycle in something that is between 1.1 and 1.9. We're actually going to take our stop milliseconds value. We're going to add in that motor front left power. And we're going to multiply that by 0.4 because 0.4 is that range in between. And that's going to end up giving us that value between 1.1 and 1.9. We're going to go ahead and do the same thing for the front right, the rear left, and the rear right value. So now we've got our drive function set up. Let's actually go ahead and control these motors in the very end. Add inside of a while true loop, after we've read all the values for our controller, we're going to go ahead and simply grab drive, and we're going to call it with throttle, strafe, and rotate. And that's it. That's how we actually program something up in Mecanum Drive. Let's go take a look and see at how this actually works around. So a brief overview of how everything works again. We set up our RC controller. Again, that's for my specific setup. You might be using a Bluetooth controller, whatever it has. We set up our DC motor controllers. We create that helper function that converts our milliseconds to duty cycles, create that helper function that normalizes joystick input, then creates that drive function, actually takes those normalized inputs and outputs it into those Mecanum Drive motor commands. We import the required libraries, create our RC object, go ahead and create our DC motors. For ours, my specific commands are stop of 1.5 with a maximum minimum of 400 milliseconds either way. We have that helper function that converts our milliseconds into a 16-bit cycle. And then we also have our stop motor function. We've got our normalizing value that allows us to keep track of dead zones. If you find this dead zone is too great or too little, you want things a little more sensitive, you can change those dead zone values. This is where we actually drive. We take in our throttle speed, our strafe speed, and our rotate speed. We check if those are all 0, we stop our motors. Otherwise, we multiply by our input scale, and then we do our actual mechanism mechanics before we check, and if anything's greater than 1, we ratio everything down before finally actually sending those motors out. So I hope you found that a useful case in converting Mecanum drive into Python controllers. If you got any questions, let me know in the comments below. And if you have ideas for future projects or other things you need help with, shoot a comment and maybe I'll make a video on it in the future. So I hope you had some fun and best of luck with your next robotics project.